Thank you, Derek.
All right, you guys, thank you for being here. I'm going to talk less about the sample selection issues and more about the data analysis issues. But we'll at least touch on this. As Jen mentioned, this came out of the work that those of us still water scientists, particularly Jody and the lead and myself, did on behalf of the Lower Columbia Fish Recovery Board and the Washington Department of Ecology, who had the concept that since there was monitoring that was to be required for the MPDES stormwater permits for the phase 1 and 2 jurisdictions in the Lower Columbia region, Southwest Washington, and there was interest in more broad-scale regional habitat monitoring to support salmon recovery, wouldn't it make sense to try and combine these into a single integrated monitoring effort? I'm not going to touch on the answer to that question, although the answer is not unequivocal, either yes or no. But definitely the more logos you get on the left side of the screen, the less likely an actual successful outcome that you guys. But you know, 1 or 2, and you're pretty well assured of having results. 10 to 15, not so much. Anyway, so I'm going to focus on the hydrologic metrics that we developed, and we didn't develop them, but we explored them and analyzed them on behalf of primarily the urban MPDES monitoring. Chris Conrad and I wrote a paper on it subsequently, and I'll be drawing a lot from that paper. So here's the area of the Lower Columbia monitoring domain, if you will. We never did actually get much participation from the Oregonians, so you can ignore everything down there. These were the overall elements of this monitoring plan. I'm going to focus on these, and again, I'm going to further focus on the hydrologic side for the urban areas, but I just wanted to give you a sense of this. And there was certainly extensive discussion and evaluation, analysis, and development of the sample site selection, which I will acknowledge but not touch on very deeply. We imagined 2 overall target populations for sampling corresponding to the 2 domains that were sort of brought together, either an inspired partnership or a shotgun wedding, depending on your perspective. The regional monitoring with a focus on salmon recovery that covered that entire area, and what was called urban and MPDES monitoring, which focused on the 8 or 9 phase 1 and phase 2 jurisdictions whose stormwater NPDES permits are coming up for renewal effective either this year or next. And so the effort by the Department of Ecology, and the reason that they funded this program, was to try and get those permittees to come together and jointly and collaboratively propose to ecology a monitoring plan, lest the Department of Ecology impose a monitoring plan on them instead. But one way or another, they were going to do some monitoring, and this was their opportunity to figure out what it was. So again, my touching on the sample population, these were the conditions that we judged were most relevant to the MPDES monitoring. Obviously, it needs to be within an MPDES regulated jurisdiction. National Pollution Discharge Elimination System, for those of you who are not in the stormwater world, so coming out of the Clean Water Act. We focused on a size of watershed that historically from other work is responsive to changes in land use and land cover, particularly urban development, and for which mitigation of urban impacts is sort of credibly applied. And of course, they basically have to be urban, which you would think might be redundant, but as it turns out, it's not entirely redundant, since, for example, the entirety of Clark County is an MPDES jurisdiction, including the parts that lie in the national park. Okay, so here's just a quick view of the segments here that we identified that met those criteria. There were a number of sites that Clark County and the City of Vancouver had previously monitored for one or another set of parameters. We call those legacy sites. We did agree to include them as a way of extending the time base of the data. I don't remember exactly how many. I think they had about 15 or 20 such legacy sites. Our goal was in each of the various combination of strata, size of the watershed, urban or non-urban land use, that we would have at least 15 sample sites in each of those strata, and we tried to also make this a rotating panel that could be feasibly afforded to monitor over the course of a 5 or 10 year MPDES permit series or 2 such series. So the actual metrics or indicators that we chose to sample were driven by a set of questions. These were the monitoring questions and objectives for the urban MPDES. I'm not going to read them all, but I will focus on this basic question. Oh, by the way, QA, like quality, and QX is flow, but I'm not sure where the X came from. This is what everybody's talked about. So QA, QX, just think water quality, water flow, discharge as the monitoring parameters. So stats and trend monitoring program, that was the requirement of the Department of Ecology. So of course our question is, what is the status and trend of quality and stream flow? That's the QA and the QX. And specifically looking at trends and specifically looking at flow, which is what I'm going to focus on today, do we see statistically significant trends over a 10-year period? In other words, once these jurisdictions are applying urban land use changes under the terms of their stormwater permit, can we detect either an improvement, which would be terrific, but we'll sort of settle for no change in the face of increasing urban development, which is the sort of fundamental goal of the MPDES stormwater permit. So this is what we're trying to evaluate through measurements of water quality parameters and in particular flow, and perhaps we also explored whether, rather than creating a full stage discharge rating curve, in other words, what you measure in a stream is the depth of the water and then go through a fair amount of effort to convert that into discharge, can we bypass all that discharge conversion and just work with the raw stage data? So that's another question that we have. Okay, these were the indicators for what we call the base program, what we thought we would recommend to everyone. And what I want to just point out here, without getting into it too detailed, is that we really focused on continuous parameters. Those of you who have been involved in water quality monitoring over the years know that the sort of traditional approach is that you send somebody out once a month, they take a scoop of water out of the stream, they run it back to cloud, and you get a typically randomly selected set of measurements from which you endeavor to infer the water quality conditions of a stream or river. We argued, based on a lot of analysis of those types of grab sample programs, is that you do not necessarily get a very representative characterization of water quality. If you miss a storm, for example, you may miss 95% of the pollutant load for the year. So we opted for those parameters that could be efficiently collected continuously with simple continuous data. And that's a question that I have saved for the end about whether that is or is not an appropriate way to go. So now I'm going to focus in on just the hydrologic metrics, that one, as a matter of fact, as opposed to the other two continuously collected measures. And again, we're trying to look at both status and trend. So for hydrology, there are those of you who played this game know that there are many, many, many different ways to skin a discharge time series. We focused on 3 of them that have been analyzed by others and really met 2 criteria. One is that they do actually respond to urban development. Actually 3. Secondly, they have a credible relationship to biological conditions in a stream. Chris Conrad, my co-author, has done a lot of work on that. Not every hydrologic flow metric actually correlates very well. A good example is annual peak discharge, right? Most aquatic organisms are used to having a flood a year. You know, big flood, little flood, it really doesn't matter to them. And so that is not a useful metric if you're interested in what has a biological response. And the last criterion is that our toolbox of stormwater management mitigation measures has to be able to have an effect on these metrics. So, for example, dry season low flows can certainly have a biological influence, almost certainly has an urban signal in it. But, you know, we don't have very many approaches these days to actually affect that. So it's really not that useful to explore whether or not we're seeing signal there. So these are the 3 that we chose. I'll give you a very quick run through on what they are, including one that's long, and I'll get to that in a moment. So here for TQ mean, the time above the mean discharge of the year, right? That's TQ mean. So here's the mean discharge of the year. Here's the time that the hydrogas spends above it. This, by the way, here's the time, of course, that it spends below it. TQ mean is this parameter, the time above the mean. And so if we look at a set of hydrographs, just 3 different alternatives for, this turns out to be 1 3. You know, the mean flow of the urban hydrograph is actually higher. And at the same time, the peaks are typically much shorter duration. So in fact, these are actual results. And this is a pretty typical range, 0.29. So smaller numbers mean a flashier and typically more urban discharge. Larger numbers typically imply a fairly sedate discharge. Sedate in terms of not as flashy. So this is one that has been explored a lot in the Pacific Northwest. Chris was actually the one who suggested this back in the early 2000s, and we've done a lot of work with it, and it's robust. It is fairly sensitive to watershed size. Bigger watersheds are just a little more languid in general, so it's important to maintain a size stratification if you're going to use it. Richard Baker Index, a good paper written in 2004, defined it. Basically, the easiest way to think about it is that you think about literally the length of the hydrograph, and obviously the peakier it is, the longer that length, and you normalize it by just the total amount of flow. So in other words, the average discharge times the time over which it happened. And so for this one, the peakier the discharge, the longer this path will be. This isn't going to change, and so bigger RBIs indicate flashier discharge. Okay, this is the one that's wrong. This is not a flow reversal definition. This is a high pulse count definition. But I've been working on another project where they've been all about high pulse counts. And so this slide, what I'm actually going to show you is, okay, so a real flow reversal is where the flow reverses. Okay, it's pretty intuitive. The one wrinkle to the flow reversal is that typically there's a threshold of change that is said, oh no, that's not really a reversal. Keith County, who drew these data from, said, you know, we're going to use a 2% threshold. So this would be a reversal. this would be a reversal, this would not be a reversal, this would not be a reversal, this would be a reversal, this would be, and so on, okay? In case you're interested, a high pulse count are these, but they're not reversals, okay? They're actually high pulse counts. We didn't do that for this study. Okay. We wanted to test these metrics. It's not enough to just define them and say these look like good ideas. And so we drew from a really substantial data set that King County has acquired over the years. You can see kind of the dates. Typically, they have a decade or more. This list is organized in a magnitude of increasing urbanization. And you can see we span quite a range of urban land development. I want to also call your attention to Sidell Creek that had a really substantial change in that urban land cover over the period. I also want to call your attention to Mercer Creek, which the USGS has been monitoring for about 60 years. So we've got sort of a bunch of decadal scale data, one with a really big land cover change over the period, and one with a really long record. So we'll kind of dig into each of these. So here's the map of these locations. They're all in King County because that's the data set that we use from, even though, yes, our work was down here in Southwest Washington. And they look like, you know, kind of like this in the low urban areas and like this in the you know, sort of moderate to high urban areas. We're not talking about concrete channels going through downtown cities, but we are talking about fully developed suburban streams. Okay, so let's just start with the basic. You know, how do these things do with urbanization? As you read these graphs, more urban that way, flashier discharges this way. Remember, the TQ mean works in the opposite direction. And, you know, by and large, with a few outliers, all three indicators respond to urban development in about the way that we would expect them to. But there's noise, right? None of them are precise. One gauge record, you can set up a spreadsheet to calculate all of them. You can also set up that spreadsheet to calculate high pulse counts or low pulse counts or anything else that you'd be interested in. And you potentially learn different things from these different indicators, although just how much remains to be seen. So one way to think about that is just, well, what's the pairwise correlation between them? TQ mean and RBI have a really good correlation. They're both measuring flashiness in about the same way. TQ mean with reversal, not so good, and we see some kind of odd outliers, which also show up here. So these are the pairwise comparisons. So they're not all identical. Whether or not you can figure out what it is you're learning from each of them, you are learning or at least seeing different things in different ones. There's no rubric to say how do we interpret it. So it means that somebody actually has to think about these and think about why is Griffin Creek different, particularly in the world of reversals relative to these flashier metrics. And I'm not going to answer that question. I'm just going to acknowledge that those questions are almost always out there with these kinds of efforts. Okay, how about the rates of change with urban land cover? We had, you know, the National Land Cover Database data for 2001 and 2011. So this is the difference in urban land cover. So, you know, Crystal Creek changed a lot. These guys didn't change at all. So more rapid, this is over the decade. And this line here, the zero line, is the change in the metric over a decade. And so you kind of look at this and say, well, that's kind of funny because some of the ones that didn't change at all, land cover-wise, actually had a fairly significant, in fact, had as much of a change as some of the ones that changed a lot. And we see that same pattern, by and large, in all three of the metrics. This is over a decadal land cover change, where with one exception, Sidell Creek, that I'll show you in a moment, you know, this is actually 5% urban land cover increase in a decade. It's apparently quite a lot for King County, although we did go through a recession there that slowed things down. And so think of this, of the spread of data here on the y-axis, is kind of the noise in the metric, right? There was no land cover change, and yet the value of the metric changed during that period. So really, we learned nothing from these metrics in terms of the influence of land cover change over the course of that decade. Now, maybe it's because our stormwater mitigation is working perfectly. But yeah, thank you. That's the right response for someone who's worked in stormwater for 30 years. You know, I think we're seeing the inescapable effect of, if you will, call it noise, but of course it's noise with respect to changing, you know, storm patterns. Presumably we're not seeing any systematic climate shift over a decade, at least none that others have identified. So this imposes a kind of limit on what we can actually expect to learn, or at least expect to demonstrate over what I would argue is a sort of management significant time scale. Okay, so here's Sidell Creek. This is 2002 when we had an aerial photograph. And this is what 15% land cover change over, in this case, 12-year period looks like. But what you'll see is that, so here's Sidell over the decadal change. Here's the averages of what I call the control sites, the ones that were over there on the left-hand side of the graph on the previous page. And, you know, Sidell, with its 15.5% land cover change, actually changed less with TQ mean and the RBI, but it changed a lot more than the reversal. It's like, what are you going to do with data like this? You're going to kind of scratch your head, and you're going to have to analyze it individually more than just statistically. Because frankly, the statistics are not telling you anything unequivocal, even with the largest land cover change over a decade of the entire data set. Okay, let's go to the Mercer Creek data, 60 years, the longest in the record. Here are the three metrics. And so they clearly show a good trend of increasing urbanization, right? TQ means that's more urban. RBI, that's going up. You know, they're all behaving like they should. And there was kind of this interesting little turn in at least one of the metrics. You can't, you know, you can kind of squint and convince yourself that it's here and here, but no, not really. But here it actually does seem to show up. And so this raises a question, which again, I would argue is not a question to answer statistically. It's a question to say, well, what, if anything, did the city of Bellevue and King County start doing in 1995? Maybe this is just Mercer Creek was largely built out by the mid-90s, and now, you know, all the trees that were cut down to line the street, you know, maybe they're starting to grow back. I mean, so it gives you pointers to think about, but it's not going to be something that you can package into a statistical analysis or anything generalizable. So it's useful, and if we had not done all three of these metrics, if you just decided maybe just do TQ mean and reversals, you wouldn't have even seen this in the first place. And I would point to that as a reason or a rationale why it is sometimes useful to have more, you know, sort of different ways, right? Like 21 ways of looking at a blackbird, right? Sometimes you see something different from one perspective. Okay, let's look for a minute at this question of stage as a surrogate for discharge. Again, those of you who are not involved in hydrologic monitoring may or may not know that it's trivial to put out a recording sensor to measure the depth of the water, but to then convert that into a discharge, you've got to have a crew going out there multiple times at different levels to measure the width, the depth, the velocity. I mean, it's an expensive process, and once you get a flood through that changes the geometry of the channel, they got to go out and do it all over again. So if we could get away with just using the raw stage data, we would actually save a lot of time and money. And in fact, if we do this for, this is the TQ mean indicator, which is not showing at the top there, it's actually not too bad. I mean, it's not great correlation, but it's good correlation. For RBI, it's crappy, right? And for reversals, it's crappy. These are all the different sites in monitoring group. So what's going on here? So let's first look at the RBI. I mean, this is a complete non-correlation. So what's going on with RBI is that RBI, because remember, it's the length of this path normalized by the amount of water. So it really matters where your datum is. And when you do stage, datum is typically an arbitrary value. You know, let's call the bottom of the channel 100. Let's call the bottom of the staff gauge, which we were able to pound into the ground 6 feet. Let's call that 0. And it's just whatever it comes up. But it actually makes a real difference, and it makes a huge difference. Our conclusion is if you normalize this with the depth so that the stage is 0 at the bottom of the channel, so you're actually having a physical measure of the depth, you can actually get a level of correlation between stage and discharge that is quite a bit more robust. It's just not the way these data are normally collected. Okay, and how about reversals? We'll look at Tower Creek. Notice that actually, using discharge, we have a range of reversals that looks like this. When we use stage, it's like all over the map. And again, there's no correlation. Remember I told you that King County and others use typically a threshold of 2%, as we're not going to count that as a reversal if the change is less than 2%. Well, this is what it looks like using that 2% threshold on the stage as well as on the discharge. But this is what it looks like when we take that threshold away. In other words, if you allow a reversal to count with more subtle changes in the stage, you actually get something that starts approaching a useful parameter. Still not perfect. And in the case of the King County data, the remaining issue is that they reported stage only to, you know, 3 significant digits, right? But we're talking about not very much of a change. And if you think about a little bit of stage change can make a lot of discharge change, right? Because the width is getting bigger and the velocity is getting faster. So a little stage change makes a big discharge change. So 2% up here is 1 degree of imprecision, but it translates into much less of a change down here in stage. And so it would require the sort of the full precision of the stage measurement to be recorded and archived. And that is not the case at the moment, which is why we still don't have a perfect correlation. But because the discharge is a mathematical function of the stage, you know that somewhere in there somebody knows what that number is. They just didn't record it in the spreadsheet. So we think that you can actually use it. And in summary, we have 3 metrics. They all seem to be useful. They do have a statistically significant relationship to urbanization. They do quantify or the hydrologic response to urbanization. But you need more than a decade to see that trend, which for managers who are hoping to apply this and actually learn something over a meaningful period, which is really a 5-year permit period, maybe 2 5-year permit periods. You know, there are problems with achieving that. And I think we can use stage, but we need to treat the data a little differently from the way we have to treat it. So that's the summary. These are my questions, and there are a few minutes for them.
Right, we started a little bit late.
That's right.
So yeah, we'll see how we go. So Derek's posed some questions. We tackle those. We don't have to answer each one, but they're good ideas from Derek. People have